Yes, Assalamu alaikum students. I wish you a very good morning, all of you. Today I welcome you to another lecture on vector calculus. It is lecture number 14. Lecture number 14, it is on surface integrals. There was a gap of a few days because I was not feeling well. So you have not received the lectures for a couple of days. Now, before I start with this surface integral, I have received some queries from some students. Their question is, we are taking sometimes the closed interval, divide that interval into small parts, then we take the rth interval, okay, and the product of the any point between the rth interval and the product of the length of the subintervals times the value of the function at that point which lies in the rth interval. Then when find out the summation of that, we get an integral, how it is. And in previous lecture I also told you, in case of line integral, if you remember, I took a curve here from A to B, then I divided this into different points, P1, finite points, P0, P1, P2. This is just what we did. It is Pi minus 1, then Pi, then you have so on to this is Pn. Then I took the length of these arcs. I took this arc. It is a general we take. And when I took this arc, Pi minus 1 Pi, I wrote it as length, suppose. Then we took the summation of this f of Pi is any point, then delta I say. We say when the subdivision points, the length of arcs tend to infinity, make the length of each subinterval 0, then that gives the integral, sum integral. In case of surface integral, we will also do the same. But the query from a student, it is okay, student has some doubt, but I would say that the student has not actually done the definition of limit, this integral as the limit of sum. It is the base that you do in your 12th class, definition of definite integral as the limit of sum, which is also known as ab initio rule for integration, first principle rule of integration, or it is known as to evaluate the integral, definite integral from definition. There we use limit of the sum. This concept is then extended. It is we can apply in the cross product form. If we take the length of the, if we take the product, cross product, if we take the dot product, all these gives us the integrals according to that theorem. I will state again that theorem so that your doubt is clear. Actually, I want to bring something from your unconscious level to the conscious level. You did it in your class 12th in integration. Sometimes we say it is a fundamental definition of definite integral. Let me state it again so that you will come to know how we use these, why it gets converted into a definite integral. Okay, let me have. It is just to review your concept. It is what you already did, so that you will come to know. This is a review of your previous work. It stated if f of x is single valued, continuous on some interval AB, A comma B are finite itself, and A is less than B, just to you say this is your interval AB, then you divide this A plus H, A plus 2H. This H is a fraction which ultimately tends to 0. Here you have A plus R minus 1H, here you have A plus RH, dash so on. You divide this subinterval. Then if you remember, then you write integral a to b f of x dx is limit h tending to 0 h times f of a plus f of a plus h plus f of a plus 2h plus so on f of a plus n minus 1 into h. This is called this one. It is definition of definite integral as limit of sum. We take the help of this definition in both in this line integral, surface integral, and next coming volume integral. There in the volume we divide the given volume into smaller volumes, and we ultimately say there in volume integral, if the volume of the rth, suppose rth interval tends to 0, when we make the subdivision volumes as infinity, when we make infinite number of these sub volumes. In this case also we will do the same definition of definite integral as limit of sum, or it is also called definite integral ab initio rule. It is also called ab initio rule or first principle rule for integration. It is actually from, you are integrating from a to b, some curve a to b. What this actually represent? You are finding here also an area. You are finding area. You did in your school mathematics. I mean by this 12th class mathematics. You did there. You have done a couple of questions on that. You see, we can write this as summation. We can write this as, in this case, it is the limit of summation, say r running from 0 to n minus 1. This is h times f of a plus rh. We can do this the way. When r is your 0, it is h f of a. When r is your 1, it is h f of a plus h. When r is 2, similarly when and finally it is n minus, it gives this one. Okay, here you have very important thing, where h tends to 0, that is ultimately length tends to 0. When h tends to 0, when n tends to infinity, this n tends, what we mean by n tends to infinity, and by n we mean the number of subdivisions. When you make the number of subdivisions tend to infinity, subintervals I mean, tend to infinity, makes the length this h 0. And here you have, and where you will have, you remember, b minus a is nh. B minus a is nh. So when h tends to 0, it gives n tends to infinity. So this is the concept that we are using for this this is actually previous concept that you did in your class 12th, definite integral as the limit of sum. We are using this in both in line integral and surface integral. I hope you have your doubt is clear, because some students are having the doubt. We are taking sometimes dot, we are taking sometimes cross, f into the length of the subinterval, where we write delta r when r tends to this infinity. Subdivision or subintervals tend to infinity, make each subinterval 0, and that gives some integral, and it is this concept that you use. Okay, I hope you have your query, this question is now clear. Now let us go to our introduction of this surface integral. Well, if you remember, in case of the line integral, we defined it there. By line integral, we mean to when we integrate a certain function on a curve, along a curve, that is known as line integral. Now here it is simple. When we evaluate this integral over a surface, that will be called as surface integral. It is definition by surface integral surface integral we mean the evaluation of integral over a surface. When we evaluate any integral over a surface, that will be called the surface integral. Now for this, let me consider a surface here, two-sided surface S. This is my, say this is surface, some surface, two-sided surface S. Now if you divide this surface into subsurfaces, you divide this way, subsurfaces you divide. So I take here a surface, this I take a surface, this is my surface. Suppose this is some surface I take, general, in other words you can say. This I take, first I write, let us consider a two-sided surface S. It is a two-sided surface S. We divide S into a finite, first finite, then this we make this finite to tend infinity, into a finite number of subsurfaces. Say it is delta S1, delta S2, delta S3, delta Sn, and in between this I take a surface delta Si. So here I am taking this surface as delta Si. This is my surface delta Si. Let us take a point here, Pi, some point in it, and it is the normal drawn. This is outward normal. To this surface N. It is in the direction of drawn normal. You know that every surface has it is normal. Now we write let Pi be any point in the surface delta Si, I took surface, where Ni is some unit vector drawn, in the direction of, it is in the direction of drawn normal. It has already some normal, every surface we draw unit vector in the direction of its own normal. Well, it is Pi any point in the subsurface we took delta Si, where Ni is unit vector in the direction of drawn normal of surface S delta Si at Pi. Then limit of the sum It is very important. Then limit of sum. What is that? Summation of, say, I running from 1 to k. I take here n, so I take here as k, doesn't matter. I will take here k. Let pi be any point in the surface s1, s2, sk I take it. But you took there, that is si. Don't worry, because we took pi now. You may not get confused, si. So we take the finite number of this, we write the limit of the sum I running from 1 to k f of pi dot delta si. But you have now pi here, I have not mentioned, I will write here, no problem, I will write here what is p, where f of p is continuous vector point function, where f of p is some continuous vector point function, because we have to take the function there. We had to take it earlier, I wrote it here, where f of p is continuous vector point function. So this sum, if it exists, this sum where k tends to infinity, limit is k tends to infinity, and each delta si tends to 0. Each subsurface tends to 0 when we make the number of subdivisions tend to infinity. When we make the number of surfaces here, infinite number of surfaces we take first a finite division, then we take it infinite, then by tending this to infinity, making infinite number of subdivisions, the each area of each subsurface tends to 0. I will write it in words. What does this mean? Where summation is extended over all subsurfaces and the, actually we have to find out limit of this. When this limit exists, it is dot here, when this limit exists, we took here ni, it is a unit vector ni, you should take ni unit vector ni. There you should also mention ni is a unit vector, this in the direction of the drawn normal. You should write there ni, where summation is extended over all subsurfaces and the limit of this summation when summation of subsurfaces tends to infinity when area of each subsurface is 0, we say the limit of this sum, it is this: when summation of subsurfaces tends to infinity, okay, and area of each subsurface is 0, is called a normal surface. It will give you an integral as per the previous explanation, is called what? It will be called normal surface integral of f. F I mentioned here. F is a continuous vector point function f of p at p is any point. P is any point on the surface. F of p means represents any point in the surface. F of p is a continuous function at any point in the surface, every point in the surface. Normal surface, our surface integral of f over our surface S, usually denoted by, it is now denoted by this way. Denoted by integral of f dot n ds over s, or you may say it like this: surface integral over the surface S f dot ds. You can denote it in this way also. Now we note here, that the surface element, this surrounding any point P, this surface surrounding any point P is considered a vector in the direction of outward drawn normal at P. Whose magnitude is now area delta S. So on the basis of this, we alternatively define the surface integral define surface integral. Now area comes, it is f dot ds. Now when we in next give you about the information that will be the, it is very convenient, very simple to evaluate the surface integral in terms of double integral. Where does double integral come? We project the given surface in any coordinate plane. When you project it in the coordinate plane, then it involves the area. That is why we say it is represented by this f dot ds. It is the prior definition. Then you will come to understand this through projection. When we project the surface in any this coordinate plane, there you will learn, you will get this s ds there. Ds is converted in dx dy, sometimes dy dz, sometimes dz dx. You will come to know this later on. So we can write this in this way also. Now let us have the physical application of this surface integral. What is the physical application of this surface integral? Why we use it? It is this. It is very important, especially for the students who are doing BTech. They have to evaluate the integral. They have to find all the applications on line integrals. I have already told you how we evaluate line integral. What does that represent? Line integral represents the work done by the force. It also represents the this circulation. That is, there we are dealing with the fluid dynamics. Here also we write here the application of this physical application of surface integral is, we write if f is the velocity of any fluid particle velocity of a fluid particle at any point f, then f dot n is the normal component it is the normal component of f, so that this double integral over the surface S f dot is equal to represents what? Represents volume emerging from S per unit time. That is surface integral measures the flux, it measures the flux of F over S. In fact, it is outward flux. In other words, the outward flux of f over the surface S is given by f dot ds. It is the physical representation of this surface integral, that is, we can use it in fluid dynamics also. For what? For this measuring the volume of the flux. It measures it measures what? Volume of flux. Per unit time I have mentioned there. This is what we mean by the surface integral. It is physical representation. But you should sometimes you will also note here, you may come across this thing. I just write remark is this. Number 1, integral S f dot ds, it is uppercase is considered uppercase of the surface. Number 2, you have integral S f dot ds, this is considered sometimes lowercase of the surface. Other surface integrals you will remember. Surface integrals we can sometimes come across surface f cross ds. It is also surface integral or integral where f is your this function, scalar function phi ds. These are also this surface integrals that we use sometimes cross or if phi is a scalar this way. Now next comes very important thing, how we evaluate the surface integral. It is actually the evaluation of the surface integral in terms of double integral. Very important, evaluation of surface integral in terms of double integral. That I already told you that when we this project the surface, given surface either in the xy plane or yz plane or zx plane, and there we can find the value of ds in terms of the this coordinate components, smallest coordinate components dx, dy, dz and so on. I hope you have understood the basics of this surface integral, and next we will come with its evaluation and application, how we apply it. Thank you very much. Wish you all the best.